Hey everyone, welcome back to my channel. So, do you know how can we convert Virat Kohli into numbers? I mean the text Virat Kohli into a list of numbers or vectors? Or have you ever wondered how these platforms like Amazon, Twitter, or Flipkart manage to understand and make sense of human language or text? How they can categorize reviews or flag inappropriate content in their platforms or recommend a perfect product, right? Even though they are just machines. Well, the secret behind this capability lies in the fundamental concept in natural language processing technique called text to vector conversion. Okay? Because here's the thing, computer don't understand the text the way we understand, right? So for them to process the text and make sense of it, it needs to be converted into a format that it understands. And how do we do that? We do that by converting text into vectors. So in today's video, we are going to dive deep into this process, exploring some of the most popular methods and techniques to convert textual information into vectors, from basic techniques like bag of words to advanced techniques like Word2Vec, TF-IDF, and transformers. Okay. Now, before we jump into the methods, actual methods to convert text into vectors, let us quickly understand why we need to do this kind of text to vectorization. As we discussed, text data is inherently complex for computers to understand, right? So, to perform tasks like classifications, search, and recommendations, it needs to be converted into numbers or vectors basically, which is a format which the computer understands. So, vectors allow us to represent words, sentences, even larger documents as numbers, making it easier for algorithms to work with them. Okay. For instance, in sentiment analysis, where Flipkart categorizes reviews, it needs to break down the text to understand whether the sentiment is positive or negative. For example, if you can see here, the reviews are categorized into latest, positive, and negative, right? To do the same, it needs to be converted into text. For example, product recommendation in Amazon, same thing. Words needs to be mapped into vectors so that the models can categorize them into different categories. So text to vector conversion is everywhere. Now let's look at the four different methods using which this text to vector conversion is done. So let's start with the basic one first. The first one is the bag of words technique. Okay. So it is one of the simplest and oldest way to convert text into vectors. So what exactly is bag of words? So at its core, bag of words is a simple method to convert text into numbers. Okay. So here is how it works. You take a text document, okay, say a review, a tweet, or a blog post, okay, and you break it down into individual words. All right. Then you count how many times each word appears. Um, Now each unique word becomes a part of our vocabulary, and it's a feature basically. And the count of that word becomes the value in your vector. So sounds confusing, right? So let's understand with an example. All right. So suppose we have two sentences. Okay, I love pizza and I love pasta. Then the second sentence you have is I love burgers and I don't like pasta. Okay. Um, Now let's build a bag of word model. So first we list out all the unique words from both the sentences and prepare our vocabulary set. Okay. So our vocabulary will look something like this: I love pizza and pasta, burgers, but don't like. Just note that we have taken all the unique words from both the documents. Okay, from both the sentences. And our skeleton vector would look something like this, which has 9 zeros basically, where each position belongs to one word in the vocabulary. Like for I we have a zero, love we have a zero, pizza we have a zero, and so on and so forth. We have total 9 zeros. Next, we count how often each word of our vocabulary, okay, appear in each sentences and take the skeleton vector and replace the count in it to prepare the final vector for each sentence. Now, for example, if we consider the first sentence, sentence number 1, which is I love pizza and I love pasta. Now, the first word in our vocabulary is I. Now, we'll check how many times I appears in the sentence 1. So, it appears 2 times, right? So, we put 2 in our vector. Now, the next term in the vocabulary is love. Love appears in the sentence was 2 times. Hence, we put 2 in it in this vector. Now the next word is pizza. Pizza appears 1 time in the sentence once. Hence, we put 1 here. And appears once. Hence, we put 1 here. Pasta. Pasta appears once. Hence, we put 1 here. Here basically. And burgers appearance is 0, so we'll leave the count as it is 0 only. But don't and like, all of them appear 0 times in the sentence 1. Leave the bits as it is in the skeleton vector. So So for sentence 1, we get this vector form, which is 221110000. Okay. Similarly, the vector representation of for sentence 2 will look something like this: 2100 and then 5 ones, because the first word in our vocabulary is I, and I appears 2 times. So we put 2 here. Second word love appears 2 times. Hence, second word love appears 1 time. So hence we put 1 here. And the third word pizza appears 0 times. Hence we put 0 here. The word and appears 0 times, hence we put 0 here. Pasta appears one time, so hence we put 1. And all the words burgers, but don't like. Burgers, but don't like appears 1 time, hence we put 1 is in the skeleton vector, and we prepare this final vector for sentence number 2. So what are the advantages of bag of words? So it is quite easy to implement and interpret, but here is the catch. I mean, it has some limitations because it doesn't take into account the order of words. For example, I occurs twice at different positions in both the sentences, but we count it at once and put it in the vector directly. Okay, so it doesn't take into consideration the order of the words that is occurring in the sentence. So it also treats common words like the, is, etc. the same as other meaningful words, which can dilute the importance of keywords, right? I mean main words in the document. So while bag of words is a great starting point, we need something more intelligent to work for complex tasks, right? So let's enter TF-IDF. Let me just change the slide. Yeah. So the next step up from bag of words is TF-IDF, or the full form is term frequency and inverse document frequency. The idea here is not to just count how often a word appears in a document, okay, but to measure its importance, okay. Now, how do we measure importance? Let's discuss. First, we convert our corpus into vocabulary as we did in bag of words model, and then we calculate the TF and IDF score for each word of the vocabulary for each document. Take each word of the vocabulary and we calculate TF-IDF score for each word of the sentence. Okay. Now, what is term frequency or TF? Now, the TF counts how frequently a word appears in a document, and the inverse document frequency or IDF considers how common or rare a word is across all the documents that is present in the entire data set. This might be sounding a little confusing. We'll understand this with an example slowly. Don't worry. Okay. To calculate the TF-IDF score for a given word, we simply multiply its TF and IDF score together. So words that are both frequent in one document but rare in others will have a higher TF and IDF score, and therefore they will be considered more important. Okay. Now let's see how to calculate TF and IDF score and how this works with an example. Okay. Let's say we have two documents. Okay, I love pizza and I love pasta. This is my document number 1 or sentence number 1 in our data set. And we have second document, I love burgers but I don't like pasta. So this is our corpus or data set or document set. Now let's consider document number 1. First we need to calculate the term frequency or TF for each word of the vocabulary for document 1. Now what we'll do, we'll pick each word of this vocabulary one by one and then calculate its TF value considering document 1. So term frequency is simple. It is just the number of times a word appears in the document, okay, divided by the total number of words that is present inside the document. All right. Now let's calculate the TF score for the word. Let's say love in document 1. So in document 1, the word love appears 2 times, and we have total 7 words, right? So the TF score for the word love in document 1 will be 2 by 7. Now for the inverse document frequency or IDF value, now IDF tells us how rare a word is across all documents. Mathematically, the formula to calculate IDF is log of number of documents with the word divided by the total number of documents. That means in how many documents the word is present and how many total documents we have. We take the division of both these factors and then take the log of this. So let's calculate it for the word love. Now we can see that the word love appears in both the documents, here and here, okay, and we have total number of documents is 2. So the IDF of the word love will be log of 2 by 2, which is log of 1, which is equal to 0. So here's the catch. Since the word love appears in both the documents, its IDF score is 0, which means that the word love is not very informative, okay. So at least not when comparing both these documents, okay. So finally the TF-IDF score for the word love will be TF into IDF. So again TF is 2 by 7 and IDF is 0. So the TF-IDF score will be 0. Alright. So this means that although the word love is common in both the documents, it's not particularly useful in differentiating between them. Okay. Now let's take a word that appears in only one document. For example, if we take the word pizza, which appears in only in document 1. Okay. Using the processes we just discussed, if we calculate the TF-IDF score, the TF-IDF score for the word pizza is 0.043 because the TF is 1 by 7 and the IDF is log of 2 by 1. So you can clearly see the TF for the word pizza will be 1 by 7 because it appears once in this document number 1. So 1 divided by total number of words in this document is 7. So 1 by 7. And the idea for this will be number of documents with the word. How many documents have this word pizza? Only one document we have. Okay, and total number of documents is 2. So 1 by 2. So the ideal value of the word pizza will be minus of 0.043. Okay, because we made a mistake in calculating the ideal value. So number of documents which have the word pizza is 1 and we have total number of documents is 2. So idea for the word pizza is log of 1 by 2. So if we multiply that with the TF score of pizza, we get minus 0.043 as the TF-IDF score for the word pizza. So the TF-IDF score for the word pizza is minus of 0.043, which means that it's more significant than love in this comparison, since it helps distinguish document 1 from document 2. So TF-IDF downplays these common words and gives more importance to rarer and meaningful words. Okay. So TF-IDF converts each document into a vector using the set of vocabulary. So similarly, if we calculate the TF-IDF score for all the words present in the vocabulary considering the document number 1, so we get the vector form of document 1, which is I love pizza and I love pasta is 0, 0, then minus 0.043, then minus 0.043, then 5 zeros. Okay. So this is how we convert an entire sentence or entire document into a vector using TF-IDF method. Okay. So as TF-IDF converts each document into a vector, just like we saw here, it converted this entire sentence into a vector. So TF-IDF is effective for the tasks that require document comparison, okay, such as document classification, similarity detection, or information retrieval. Search engines use TF-IDF technique to rank similar documents based on the search query. So that is how TF-IDF works. So now let's move into the next method, which is word embeddings. Okay. So till now we saw two methods which converted the entire document into a vector, right? The entire sentence it converted into a vector. Now we'll understand a method which will help us in creating vectors for each individual words in a corpus, right? So TF-IDF improves on bag of words method, but it still does not capture the meaning or context of the words. So this brings us to the next level, which is word embeddings. Okay, so the third technique is word embeddings. One of the most famous methods to implement word embedding is Word2Vec. Okay, so there is a technique which is Word2Vec. Okay, so unlike bag of words and TF-IDF, Word2Vec does not just count words, it converts words into dense vectors, where words with similar meanings are close to each other in the vector space. Mark this what I said, okay? It converts words into vector. So TF-IDF converts the entire document into a vector as we saw, but Word2Vec converts each word into a vector. So both have their own real life use cases anyways. So Word2Vec captures semantic relationship between two words. For example, in Word2Vec, the vectors for king and queen will be closer together, and you will see interesting relationships like king minus man plus woman will be equal to queen. Okay. Now how Word2Vec works actually. So Word2Vec comes in two main flavors, CBOW and skipgram. So CBOW is continuous bag of words. So we have two techniques to implement Word2Vec. Okay. So CBOW tries to predict a target word based on the surrounding context words. Okay. So given the sentence, the king is ruling the kingdom, CBOW will try to predict the word king. Okay. By looking at the words, neighboring words like the, then is, ruling, etc. Okay. So CBW is essentially asking what word should go in the middle based on its neighbors. Okay. Now the skipgram model is just the opposite. Okay. It does the opposite. Given a word like king, Okay, it tries to predict its surrounding words. So the king would be used as the input word, and it will be used to predict the surrounding words like the, is, ruling, etc. Okay. Now, how many neighboring words do we need to consider? So that is determined by the context window size. For example, if I take a window size of 1, I'll consider one left and one right side of the word for a given word. And those will be my context words. Okay. For example, if king is my target word, then the word to its left, that is the, and the word to its right, that is. Those will be my context words. Okay. So now let us understand CVW with an example now. Let's say we have a list of sentences or corpus like this. Okay. I love dogs very much and dogs are great. So these are the two sentences or two documents in my corpus. So first we prepare a vocabulary for this corpus, which is nothing but a set of unique words, just like we did in bag of words and TF-IDF. So my vocabulary looks like this. I love dogs very much, are, and great. Okay. And the skeleton vector for this looks like this, which is 7 zeros. Okay. So 1 0 for each word in the vocabulary. Alright. Next, we prepare a list of context words and target words pairs. Okay. Taking a context window length of 1, that is taking one word left and one word right to the target word, will have pairs like this. For example, if I take the word love here, its context pair will look like I and dogs. So I and dogs are the context words. For the word dogs, the context word pair will look like love and very, right? One left, one right. So love and very, and so on and so forth. We can prepare this kind of target word and context word pairs. Okay. Now let's take the first pair. For example, love and I dogs. So the target word is love and context word is I and dogs, right? Now we'll use one hot encoded format for these target words and context words. For example, the one hot encoded format for this word love will look something like 0 1 then all zeros, because if I use the vocabulary set, um, love is present as second index, hence we set this position to 1 and rest other bits are set as 0 only. So this is my one hot encoded format for the word love, and the one hot encoded format for the context word, that is I then dogs, is 101 then 40, because I is present here, so 1 will be set here, then this is 0, then dogs is present here, hence 1 will be set here, then all other positions are set as 0. So this is my one hot encoded format for my context word. Okay. Now this context word vector, now this context word vector becomes input to our neural network, and the target vector is our desired output. Okay. If you see here 101 then all zeros, this is the vector one hot encoded format for my context word, that is I dogs, and 01 then all zeros is my one hot encoded format for my target word love. Okay. Then we train a neural network like this with this type of context words and target words vectors, and generate intermediate weight matrix. So you can use more than one hidden layer in our neural network also. That is fine. So here we are not going to understand in details how a neural network works. Okay, else this video will become lengthy. So once the network is trained using gradient descent algorithm, these weights that connects to this hidden layer, okay, which is also known as the embedding layer. These weights help in computing the word embeddings, which so these are my word embeddings. Okay, 0.34 minus 1.34. These numbers that I have taken, these are my word embeddings, which help in capturing the contextual relationship of a word and help in converting a word into a word embedding. Okay, so now this word embedding represents the vector form of a word. The size or dimension of this embedding layer depends on the vocabulary size, the corpus size, and the task that we are trying to solve. Here we have taken a dimension of 6, right? We have total 6 nodes in this embedding layer. So dimension of our embedding, word embedding is 6 here. Okay, so I'll attach a link to the Python code in the description, which implements Word2Vec from scratch in Python. Okay. If you can see here, after we train this neural network, we will have this set of weights which is marked as W1. Hence this W1 weight matrix will help us in converting a particular word into vector. For example, if we want the vector format for this word very, so we'll take the one hot encoded format of its context word, which is dogs and much. Okay, we'll take that as input, we'll multiply that with this weight matrix, and we'll get the embedding vector. We'll get the word embeddings for this word very. Okay, so this is how we convert each single word into a vector format in word embeddings technique using Word2Vec and continuous bag of word model. Okay. So yeah, this is how Word2Vec works in CBOW method. Skipgram method also works similarly like this to find the vector representation of a word. Now let's move on to the next technique. Okay. Finally, we arrive at the state of the art method for text conversion or text vectorization, which is the transformers. So one of the most popular transformer models is BERT, okay, BERT, which is nothing but the bidirectional encoder representations from transformers. So we have a popular transformer model which is called BERT actually. So what makes BERT and transformers unique is that the context understanding capabilities of transformers is much deeper and more accurate. Okay, they hold more context than even more than Word2Vec model. Okay, so for example, take the word bank in the sentence. I went to the bank of the river. So BERT knows that bank refers to a river bank, not a financial institution or financial bank. But if you look at the second sentence, I deposited cash in the bank. Here BERT will again understand that this word bank in this sentence refers to a financial institution, not to the river bank. So how does it do that? It does so because it looks at the entire surrounding words, okay, not just one or two neighboring words, which was in the case of Word2Vec. So transformer based techniques produce dynamic embeddings based on the context of a sentence, which is not the case in Word2Vec because Word2Vec produce static embeddings. The embeddings generated for the word bank would be same in both the scenarios in case of Word2Vec. But in transformer based techniques, they tackle this problem and solve this problem efficiently by generating dynamic embeddings for the same words in different scenarios or in different documents. Okay. Now, how does BERT works actually? So it converts the entire sentence or even paragraphs into vectors by encoding the relationship between all the words in the text. I'm emphasizing on the phrase all the words. Okay, it considers all the words present in the text to generate vector embedding for a given word. So this gives us extremely powerful text representations for tasks like question answering, text classification, or even translation. Right. So that is why transformers are more powerful even than word embeddings techniques. So transformers are currently the gold standard for NLP tasks. So as they are used widely in platforms like Google Search, where deep understanding of user queries is crucial. Even the T in ChatGPT stands for transformers because ChatGPT also uses transformers based techniques. Okay. So we'll create a separate video to understand the technical details about how a transformer works in NLP because it will need some explanation. So the video, it needs a separate video for to explain the things in detail. Okay, so we'll create a separate video about that. So there you have it. We have gone from simple word counting in bag of words to weighing word importance with TF-IDF to capturing word meanings with Word2Vec, and finally we explored how transformers like BERT are modernizing text vectorization by understanding the context at a deeper level. Next time when you use a search engine or get recommendation in Netflix or even interact with a chatbot, remember that the core of all these are machines translating text into vectors to understand what you mean. Okay, so if you found this video helpful, don't forget to like, subscribe, and hit the bell icon for more insights into the world of AI, NLP, and machine learning techniques. So we are targeting to reach 250 subscribers by the end of this month. So keep supporting. So thanks for watching and see you in the next video.